All right, if you're gearing up for the Cambridge 9702 physics exam, we are cutting out absolutely all the fluff today. We're diving straight into the fundamentals of materials. Specifically, we're going to lock down exactly how you link band theory, carrier motion, and material classes to secure those top-tier marks. So picture this for a second. You are sitting in the exam hall. That clock is aggressively ticking down. You flip the page and you see a question asking you to explain the basic differences between materials. And suddenly, you completely blank. Why do so many incredibly well-prepared students just freeze up on what seems like a simple 3-mark classification question? Well, it happens because of a very popular but incredibly dangerous revision shortcut. And it absolutely backfires. Look, memorizing basic vocabulary words like insulator or semiconductor without actually understanding the underlying physical mechanisms, that is a massive trap. Honestly, it's a one-way ticket to losing crucial grade boundaries. Ordinary revision just completely fails here because examiners are not looking for simple labels. To actually secure those top marks, you need a massive mindset shift. Conductivity is not a simple yes or no label. It is a direct physical consequence of a material's internal energy structure. Specifically, we're talking about the gap between its valence band, where electrons normally hang out, and the conduction band, where they are actually free to move. If you're going into the exam treating materials just as things that conduct and things that don't, you are completely missing the physics. Okay, so how do we fix this? Here is your first quick win. Whenever you revise this chapter, you need to anchor your thoughts to 4 specific prompts. 1, definition. 2, microscopic cause. 3, macroscopic consequence. And 4, real application. Seriously, if you can just talk through these 4 steps in order, you can reconstruct a top-band exam answer literally no matter how they decide to phrase the question. And hey, in just a minute, I'm going to reveal the exact examiner command word that magically flips a basic 1-mark answer into a solid 3-mark answer. But to actually spot that clue, we first need to build a rock-solid physical framework. Let's build that physical picture right now. The concept of a whole is entirely central to this entire topic. Now listen closely. Do not, under any circumstances, present a whole to an examiner as just an empty space or a formal absence. No, it is a dynamic, incredibly useful physical model. It represents a missing electron, sure, but its behavior can be treated dynamically. It describes exactly how charge transport behaves in certain solids. And understanding that is what perfectly sets up the critical comparison you need to make. When you're comparing an insulator and a semiconductor, you have to use cause and effect reasoning. An insulator naturally resists charge motion. Why? Because of its wide band gap. A semiconductor, on the other hand, allows for controlled conduction via specific available charge carriers. Like those dynamic holes we literally just talked about. Now, the real-world consequence of that physics? It's fascinating. By understanding this idea of controlled conduction, we bridge the gap between pure physics and everyday electronics. Just a few small structural or compositional tweaks can take a material from being a boring basic insulator and transform it into the highly responsive core of a switch, a complex sensor, or even a computer processor. So the physics is super cool, right? But let's decode the actual exam rubric. How do Cambridge examiners actually want you to write this stuff down when you're sweating under the pressure of the exam hall? How do we take these abstract concepts of holes, bands, and conduction and format them into a guaranteed A-grade response? Here is the exact stepwise reasoning you need to lock in. It goes concept to evidence to scientific reasoning. In practice, this means first, you identify the material class. Second, you explain the allowed carrier motion, or hey, what blocks it. And third, you connect that motion to a technological consequence. You have to chain these ideas together physically. Don't skip steps. Let's do a live makeover on a typical answer. Here's an incredibly flawed but super common student response. Semiconductors conduct electricity sometimes. Yeah, that gets you basically 0 marks. Now look at the top band version, using mechanism-rich language. Controlled conduction occurs due to band energy structures, specifically electrons jumping the band gap to leave available holes. Boom! That is the exact wording and depth the examiner is begging for. And look, if you don't believe me, let's go straight to the source. Let's look at an actual examiner report. They specifically wrote, a frequent weakness is to name semiconductor correctly, but fail to explain why it is different from an insulator in usable terms. See, if you don't explain the why, the actual carrier motion and the energy bands, you just bleed marks. All right, it is time for a quick topper autopsy challenge. I want to see if you've actually internalized this framework. I'm going to give you an incomplete answer from a student who's trying to explain how a material is used in electronics. I want you to spot the exact logical link they carelessly left out. Ready? Here is their flawed logic chain. Point 1, the material has specific bonding. Point 2, well, that's the missing link. Point 3, therefore it is used as a solar cell. Take a second. What massive conceptual leap did the student just make? What is supposed to go in that middle spot? If you grabbed your metaphorical red pen, you should be circling that gap and writing carrier behavior. You absolutely must state what blocks or allows charge motion. You cannot just jump from a material's basic structure straight to its electronic function. You have to explain the actual mechanism sitting right there in between. And honestly, this mechanism is everywhere. When a question asks you to provide real-life applications in your answers, you now have a bunch of exam-ready links. Phones, computers, traffic control electronics, solar cells, LEDs, sensors. Every single one of these depends entirely on specific material classes and their carrier behavior. So the crucial takeaway here is that in the real world of engineering, this isn't just abstract vocabulary to memorize. Choosing a packaging insulator versus a highly calibrated sensing surface, that's never an arbitrary choice. It comes directly from understanding these fundamental material behaviors. That is exactly why this chapter is so significant, and it's why examiners test it so rigorously year after year. And by using this cause and effect reasoning, you've just confidently secured 3 crucial marks on what is arguably one of the toughest descriptive questions in the entire syllabus. You aren't just naming things anymore, you're actually explaining the physics. Okay, let's do a rapid-fire recap of the stepwise reasoning that's going to stop you from blanking under pressure. Step 1, identify the internal structure and bonding. Step 2, define the carrier model. Remember those dynamic holes we talked about? Step 3, state the electronic function or macroscopic consequence. Just remember, structure, carrier, function. All right, checkpoint time. After walking through this explainer, can you explain the concept of a hole back to me in your own words using those 4 anchor prompts we discussed? Definition, microscopic cause, macroscopic consequence, real application. Seriously, try it. If you can do that right now, you've officially mastered this topic. But, as always in Physics 9702, mastering the theoretical framework is only half the battle. You now possess the absolute ultimate blueprint for answering materials questions perfectly. But there is still one massive, entirely unresolved problem lurking in your next past paper session. Because look, knowing the physics is step 1. But how do you actually deploy this beautifully structured answer when the exam timer is literally breathing down your neck? How do you survive the brutal time control traps that examiners deliberately set up to ruin your pacing? You've got the knowledge now, sure, but without the right time management system, you're still going to lose marks. And that brings us to your mandatory next steps. You need to master the time control system to pair with this framework, and you need to decode the rest of those tricky examiner traps. If you want to absolutely excel in your Cambridge examinations, make sure to subscribe to the Ace the Exams YouTube channel at aceexams_IGCSE. We're breaking down all of it. Please do not let your perfectly structured materials answers go to waste just because you ran out of time at the end of the paper. Click the next explainer on screen right now to unlock the complete time control system. This is an absolutely essential next step before you even think about tackling another 9702 paper. Go click it, and I'll see you over there.